I had mentioned to you folks previously that we will be combining chapters 1 and 2 together as a unit, and we will be tested on that before we move on to chapter 3. So today we're going to be actually starting chapter 2. We're going to be doing a little bit of number theory. I call it number theory 101. And I'm going to go through permutations and combinations pretty quickly, okay? 99% of the work you do with permutations and combinations will be done on your calculator, and as long as you can find the proper buttons to push on your calculator, you should be in pretty good shape. But I know what's coming in chapter 4. Chapter 4, we really get into probability pretty heavily, and you desperately need to understand this for chapter 4. So that's why I'm kind of giving you a bit of a head start here today with regards to the number theory problems. So anyway, let's get started. On your homework, you had some problems with trying to find the number of groups of 2 people that are gotten out of 5 people. So here are your 5 people, A, B, C, D, and E. And here are the groups of 2 people, like committees of 2, okay? This was demonstrated in the homework, and to figure out that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these, to figure out that there are 10, in your homework, you had to list all the various possibilities. So the question is there a way we can figure this out without listing them all? Okay? Notice we are using the basic counting rule here. We are not replacing. Okay? Like for instance, when you pick person A to be on a committee, you don't put him back in to pick another person. You can't pick person A twice. Once he's picked, he's done. He's picked. Okay? All right. Let's talk about putting books on a shelf. How many different arrangements are there of putting 5 books on a shelf? In other words, you have 5 ways you can pick the first book. Then you have 4 because we're not replacing. Then you have 3, then you have 2, then you have 1, okay? Or you have 5 times 4 times 3 times 2 times 1. There are 120 different ways you can put 5 books on a shelf, okay? Something as simple as when you have A, B, C, D, E, just switching the B and the A, B, A, C, D, E is a different arrangement. So there's a total of 120 different ways that you can put 5 books on a shelf. This is written, when you do 5 down to 1 multiplying, it's written as 5 with an exclamation point. And this is stated 5 factorial. 5 factorial gives you the number of different arrangements. Now, let's actually do it with 3 books. According to what I just said, what should the total number of arrangements be? There's 3 ways to pick the first, then 2 the second, then 1 the third. 3 times 2 times 1, there should be 6. Let's see if we can get it. ABC, ACB, and I guess that's it. BCA, BAC, CBA, CAB. And there are all 6 different ways that you can arrange 3 books on a shelf. 6 different ways. 10 books with a 10 factorial arrangement, 7 books, 7 factorial. We get into some pretty big numbers. Can you find that on your calculator? Let's take a few minutes and talk about that. If you have any problems with trying to find this on your calculator or finding this on your calculator, make sure you contact me so I can help you out and find the proper buttons to push to get this figured out. All right, let's see if we can come up with a formula for this. Suppose you had 5 books and you had space for only 2. All right, now one way to do it is, if you had 5 books with space for only 2, you have 5 times 4, okay? Another way of looking at it is 5 factorial is 5 times 4 times 3 times 2 times 1. If you just want 5 times 4, I have to get rid of the 3, 2, and 1. 3, 2, and 1, is it not 3 factorial, right? Which is 5 minus 2 factorial. If you do that, 5 minus 2 gives you 3 factorial, then they cancel, and you're left with 5 times 4. And that is where the formula comes from for finding the total number of arrangements is n factorial over n minus r factorial. When you are going for arrangements, okay, this is called a permutation. Permutation. Okay? Permutations, the rule n factorial over n minus r factorial is an NPR. This is the total number of books, the letter N. R is the number of spots you have to put the books on the shelf. Okay? So can you find the NPR on your calculator? You need to be able to do that to be able to do permutation problems. All right, so how many arrangements are there? 5 books out of 9. You want to do a 9P5, okay? Or by the formula, it is 9 factorial over 9 minus 5 factorial, which is 4 factorial. This cancels the 4 times 3 times 2 times 1, and you're simply left with 9 times 8 times 7 times 6 times 5 on the top, okay? All right, but can you find it on your calculator? So what I'm going to do is a 9P5, and you should get 15,120. Okay? 15,120 different ways of putting 5 out of 9 books on a shelf. Quite a few different arrangements. All right? Now, permutations are written NPR, where the R is the number of spots. This is the total number of books, okay, or anything that you're arranging. Now let's talk about committees. Okay, suppose there were 5 people and you wanted committees of 2. Okay, this is back to what we did here. 5 people and you want groups of 2. Okay, is there a way to do that without listing them all? If you have 5 people and you wanted committees of 2, we know that there's 5 factorial over 5 minus 2 factorial arrangements. But arranging 2 different people in a different order does not create a different committee. So you have to divide out. Like, for instance, AB is the same as BA for people on a committee. So to get the correct answer, when you do 5 factorial over 5 minus 2 factorial for arrangements, permutations, you then have the total arrangements. These are different arrangements. You want to divide that out. So this cannot happen. How many ways can you arrange 2 things? 2 times 1 or 2 factorial. So the formula for a committee is an NCR, which is going to be capital N or small, it doesn't matter. N factorial over N minus R factorial gives you arrangements, and then also divide by R factorial, and you will get the committees. And so here are the 2 formulas. But once again, you're going to do 99% of these on your calculator. You really, I hate to say this, you really don't need that. You just need to know how to find those things on your calculator and understand when to use permutations and when to use combinations. Okay? So these are combinations. NCR are combinations. Okay? Combinations. How many committees of 4 are there out of 6 people? You need to do a 6C4. 6C4 should be 15. You should be able to get 15 different committees out of 6. You're going to find out very quickly that there's always many more permutations or arrangements than there are combinations, okay? Because just rearranging a committee, it's still the same committee. How many ways can 3 people be selected out of 5? That would be a 5C3. And doing a 5C3, and I get 10, okay? Just like picking 2 people out of 5, picking 3 people out of 5, you get the same amount, which some people have a little problem with that. I'm going to say it again. If you pick 2 people out of 5, you get 10 committees. If you pick 3 people out of 5, you also get 10. Why? Because every time you pick 2, the 3 people that are left over are their own little committee. Are you with me? So every time you pick 2, the remaining 3 is a committee. So the number of 2s that you pick will also be the same as the number of 3s. And that works all the time, okay? Whether you're picking 4 people out of 5, that should be the same as picking 1 out of 5, because every time you pick 4, there's 1 left over, and so on. All right, how many ways can 3 people out of 5 win a red, blue, or white ribbon, hold everything? This is horribly different. If you have a committee of people A, B, and C, that committee is the same whether it's C, B, and A, right? But if you're giving red, blue, or white ribbons, A, B, and C, the arrangement is going to be critical because the first person named will get the red, second gets the blue, you see? So for this one, it's got to be a 5P3. 5P3, and what is a 5P3? Is 60, okay? So a 5C3 is 10, a 5P3 is 60. How many ways can committees of 0 be selected out of 5? How many ways? It's a 5C0. You can work it out. But how many ways can you do committees with nobody on it? There's only one way you can do that. You don't pick anybody. You don't pick anybody. That's one way. Do that on your calculator. You should get 1. How many arrangements of 5 books on a shelf? That is a 5P5, which we already did, and I think we said that was 120. How many arrangements are there of 3 elements out of 7? That is a 7P3, because it's arrangements. Grind it out. A 7P3 is 210 different arrangements of 3 out of 7. Okay? Oh, what is this? You should check us out. We're the fastest growing religion in the country. Fastest growing, kind of a dubious claim. It's true. We grew by 85% last year. Hey, Rob, you want to join my religion? Sure, whatever. Well, it looks like my religion just grew by 100%. 1 went to 2, that's 100%. We have 38,000 members. Hope you're okay with second place. 85% is not 100%. I love that. I thought that was great. What is this? When you look at this chart, that's right. When you look at it this way, it's not so bad. Looks like sales are going up when you have the chart laying on its side, right? Okay, misleading graphs. Let's talk about them. This is a big deal. Notice here on the y-axis how we go 0, 4, 8, 12, 16, difference above 4 each time. Perfectly done. Snowfall from 2001 to 2002, right? Looks good. But this is the same data. In 2001, it's 16. In 2002, it's 24. Same data, but it looks so much worse. It looks like 2002 is horribly, horribly ahead of in snowfall, and it's because look at the scale. Now, granted, they did put the squiggly line in there to show you that we're jumping over numbers, but still, this is very misleading when you don't do a consistent scale on the y-axis. Horribly, horribly misleading. This was in the Daily Item, Sunbury Daily Item, local newspaper on Monday, October 8th, 2018. Another statistics professor brought this to my attention. I said, this is ridiculous. We wrote a letter to the paper and told them it was ridiculous. In fact, we redid the data in a bar graph to make it correct. They printed our letter, but they didn't reprint our bar graph because they wanted this to look astonishing, that the number of high school football players is decreasing, okay? It looks like if you go down over here, and if you actually measure these bars, it looks like it's almost an 80% decline. And it looks horrendous. But notice, this is not starting at 0 and going up to 26,000. It really only goes from 26,900 to 25,600. If you do the math and figure it out, it's only about a 4.8% decline. Extremely misleading to not have it go from 0 up to the total. Okay? Oh, why does it do that? Pop-ups. I hate pop-ups. Here's another one. I got this from Chevy trucks. More than 98% of Chevy trucks are still on the road. Look at these. Ford, Toyota, Nissan. Look at how horribly they go down. Doesn't start at 0. When it starts at 0, look at it. It looks like it looks like they're almost all the same. And that's why they do that, to make it look more exciting, just like the football numbers. They knew that would attract a lot of attention if they had that graph done in such a way to look like a horrible, horrible decline. Here's another thing that's misleading. When you do something on ticket prices, okay? Look at the size of that baseball. I mean, that baseball looks like 4 times as big as that, when in actuality, the price goes from 10 to 20. It's only twice as big. This one is 20-something to 50-something, twice as big, but because of the size, it makes it look so horrendous. This harkens back to an old fun math problem. If you have a 6-inch drain pipe and you have a 3-inch drain pipe, how much more water will flow through this one than through this one? 6-inch drain pipe, 3-inch drain pipe. What's everybody say? Twice as much water. It's 6 instead of 3. No way. It's technically 4 times as big. You could put the 2 3s in here, see? One right on top of the other one, then you have all this area on either side. It's actually 4 times as big water that flows through a 6-inch drain pipe as compared to a 3. No extra charge for that. That was just kind of fun. All right, let's move on into chapter 2 now. Talk about a few things in chapter 2. Variables. Your data can be anything that varies from one person to another. Numerical data is called quantitative. Non-numerical is qualitative. I mentioned that on our first class together. Quantitative could be like weight, age, height, and so on. Qualitative, eye color, hair color, favorite food, right? By the way, Zip code is qualitative. You might say, whoa, a zip code has numbers. Well, yeah, it has numbers, but you can't do any mathematics on a zip code. You can't figure out the average zip code. That doesn't make any sense, okay? Numerical data such as zip codes or birth dates should be qualitative. How about grades at SU? Letter grades, right? Qualitative. Percentage grades would be numerical, quantitative. Now, once you start talking about quantitative data, numerical data, discrete variables is data which can be counted. Usually it's whole numbers, counted. Continuous variables are decimals and somewhat indeterminate in length. I'm not going to make a big deal out of this, okay? You're going to have a couple of homework problems on this. I highly doubt if you ever have anything on a test about this, okay? Number of people, right? Discrete. Height of a child. Continuous, because it's going to be not whole numbers. Time of the 100-meter dash. Continuous, decimals. Number correct on a quiz, discrete, whole numbers. Okay? Not a huge deal. Homework. You've got a couple of sections of problems in the book, here and here, as we finish up chapter 1 and then go to chapter 2, and the number theory problems, okay, that will be in Blackboard, that you can get those.